So now we've got a bunch of equations here we're going to solve using the change of base formula. Oh, and we'll do a little modification of that too. But what I can do is, now that we know about how to use change of base, and we can change, we've got this equation, I've got this 2 to the x equals 10. Well, I can't raise 2 to some power and get 10. So we need a new technique here. And one new technique is, well, if we can't solve this exponential, let's write it as a logarithm. That's always something to try. So I know the base is 2. So my equation become log base 2 of 10 equals our x. Well, boy, that looks just like our change of base formula. So that's what we're going to do. We're going to do log base 10 divided by log of 2. Log of 10 divided by log of 2. An exact answer would be 1 over log 2. And the decimal approximation would be just to calculate that on your calculator. So we're going to do 1 divided by the log of 2, and that didn't work. Clear. 1 divided by log 2, and that's our decimal approximation. Okay. Now, there's one other way to solve this one, and I hate to confuse you throwing you two ways at once, but I'm going to do this because sometimes people forget this, and they usually remember this method. So here I've got this equation, 2 to the x equals 10. Well, I can't rewrite it. So what I'm going to do is I can take the logarithm of both sides. I can also do the ln of both sides. As we learned before, it doesn't really matter. So if I take the log of both sides of this equation, then I can use that exponent property of logarithms to bring that x down in front. So I can say x times the log of 2 equals the log of 10, but log of 10 is 1. So then if I divide both sides by, I'm going to solve for x, so if I divide both sides of this equation by log 2, notice how I'm getting the same answers. Okay? So that's another way to think about this. You could just take the log of both sides, bring the exponent down in front. I like the change of base formula when I can, but I'll use both ways. So, two methods, same problem. Let's look at another one. So this one, not quite so nice because I missed one. Sorry, just a minute. Let me find it. Here. Here's the example from the book. So we've got this word problem. We're looking for when will the population of India equal 2 billion. So, I mean, if you look at the example in the book, they've already done this for you. We know that we're looking for where this equation is equal to 1.14. I'm going to add those two together. So the variable I'm looking for is t, so I need to be able to, that exponent, so I need to probably use logarithms to solve this. If this were just 1.0134 to the t power, that'd be easy. Take the log of both sides or change a base or whatever. So that's what we're going to do, is we're going to try to make this equation be that. So the first thing we're going to do is we're going to divide both sides of this equation by the 1.14. Okay. And let's fire up the calculator and take a look at that. It's equal to. So 2 divided by 1.14 is 1.75. So I know that 1.754 is probably enough decimal places, equals this expression now. So now this problem is just like what we just got done doing. We can rewrite it, change a base. We can take a logarithm both sides. I think I'm just going to rewrite it as change base formula, since it is just fairly simple. So the base is 1.0134. You know, the answer is 1.754, and that's equal to t. So I'm just going to apply the change of base formula. Take the log of 1.754, divide that by the log of 1.0134, and that'll be the time. In years, now I think we might have to do a little bit more to this problem in a second, but let's get that decimal. So the log of 1.754 that in right, I got 42. Okay, probably should go back and take a look at this problem. They want to know when will the population reach 42 billion. So we know that it started in 2008. So what this problem is going to ask us to do, I'm pretty sure of it, is to take 2008 and add 42.2 years. So we can say that during the year 2050, the population of India will reach 2 billion. Okay, so that's that problem. Let's see, what's another one? So here's now you try it problem. So again, I'm going to pretend you're stopping this video and try to solve this. This is just like that other problem, except there's no application to it. I'm try to isolate that x. So I'll stop for a minute and you try it and I'll solve it. So I'm assuming you solved it and stopped it, and I'm just playing this through. So I'm going to divide both sides by 5 because I want to get that logarithm by itself, or get that exponent by itself, that base and that exponent by itself. So that's going to be equal to 2. And so now I'm just going to use the change of base formula. I'm going to say x equals log of 0.93 because that's the base of 2, and I'm just going to apply the change of base formula. Log 2, change it to base 10, log 0.93. I could also use ln. Let's try to hide all that. There we go. There. So log 2 divided by log of 0.93. Notice the parentheses I'm using on this. Okay, that does cause some problems if you don't use the right number of parentheses. I've got to close this right here. Okay. So let's see. I'm going to enter. So x is negative 9.55. That is different. That isn't what I was expecting. Would be, if this were in time, if this were talking about population, it would be 9 years in the past, almost 10 years in the past. And if we look at that, yeah, I'm just going to think about this. That initial value is 5, and we're looking for, when this is the decay equation, so we're looking for when in the past it was equal to 10. Interesting, interesting. But that's how you solve that question, okay? Is that all the problems we've got here? All right, I hope that helps. Try some more in the book.